Hello students. So today we're going to solve two problems in Archimedes principle. The first one is this. We have a cubical block of wood. It doesn't matter what the shape is, but if its relative density is 0.6, that means its density is 0.6 times the density of water. Now we know that if we float it on water, it would float with 60% of its volume submerged and 40% outside. But this block is attached to a spring, and the spring is attached to the ground here, and we are told that it's 80% submerged. That means it has been pulled down. Now, a compressed spring pushes, a stretched spring pulls. So right away we know the spring is stretched. Now, if you don't quite understand that, look at it this way. We have the block floating with 60% submerged. We have a spring it is attached to the floor and it doesn't quite reach the block. Now I pull the spring and hook it onto the block. So the stretched spring pulls the block down by a further 20%. So it is a stretched spring, and let's say the amount by which it is stretched is x meters. Let's look at the forces acting on the block. First, there is the buoyancy. Next, there is the weight of the block. And thirdly, there is the force exerted by the stretched spring. Let's write down each of these forces. The buoyancy is the volume of the liquid displaced. So that is 80% of 1 cubic meter, so 0.8 cubic meters. We want the weight of the water displaced, so this is the volume of the water displaced multiplied by density of water, 1000 kilograms per cubic meter, multiplied by g. I'll take it as 10 meters per second squared. This is the buoyancy force. That is equal to 8000 newtons. Now we have the weight. For the weight, I have to use the total volume of the block, 1 cubic meter, multiplied by the density of the block, 0.6 times the density of water. That gives me the mass of the block, multiplied by g gives me the weight of the block, and that's equal to 6000 newtons. And lastly, we have the force exerted by the spring, which is the spring constant, 800 newtons per meter, multiplied by the amount by which it is stretched, x meters. Since it is in equilibrium, the net downward force is equal to the net upward force. So net upward force is 8000 is equal to 6000 plus 800x. So that gives me 2000 divided by 800 is equal to x, and simplifying that we get x is equal to 2.5 meters. Next problem. So let me remind you, it's the same block, 1 cubic meter, and relative density of the block is 0.6. It's now floating with 80% underwater. So that means 0.2 meters is the height of the block above the surface of the water. And the spring is extended by 2.5 meters. We solved this recently. So there's an extended spring which is pulling the block down. Now at this point, what we're going to do is start loading mass on top of this block so that the block gets just fully submerged. And the question is, how much mass m do we add? So when the block is fully submerged, the upward buoyancy force is going to be 1 cubic meter. That's the volume of the block, which is now the volume of the liquid displaced, multiplied by the density of water gives me the mass of the fluid displaced, multiplied by g gives me the buoyancy. Now the buoyancy is 10,000 newtons. That's the upward force. What are the downward forces? The downward forces are the weight of the block, the pull of the spring, and mg, the weight of the masses I have placed on top of the block. And since it is floating, the buoyancy is equal to the net downward force, which is the masses that I have placed multiplied by g, that's the weight of the masses I have placed, plus weight of the block. Now how do I find the weight of the block? I take the volume of the block, 1 cubic meter, multiplied by its density, 600 kilograms per cubic meter. This is the mass, multiplied by g gives me the weight. So that is 6,000 newtons, the weight of the block, plus the pull of the spring, which is spring constant 800 multiplied by how much? Now remember, initially the spring was extended by 2.5 meters. Don't confuse this with this arrow. This arrow is the force exerted by the spring. The spring was extended by 2.5 meters. Now it comes down by a further 0.2 meters. So the spring is now extended by 2.3 meters. That's the K times X is the pull of the spring. So let's solve this for M, and M turns out to be 216 kilograms. That's it for today, folks. Bye-bye.